If you're a parent, or if you have parents, then you know what the talk is. That's that moment when you have to have the discussion with the young ones about human procreation, the birds and the bees. Now, I really have no idea how we came up with that as the metaphor, the birds and the bees, because neither birds nor bees reproduce the way humans do, but that's the metaphor, and so it's not up to me to mess with that. It is up to me, though, to check to make sure that the sound system is working okay and that you can hear me all right in the back. Excellent. 5 years ago, a little more than 5 years ago, my wife and I adopted a couple of boys from Haiti. And I was sitting downstairs in the basement, minding my own business, watching a Nationals game. That's right, the Washington Nationals in the World Series. She came down the basement stairs with the boys with kind of a wicked gleam in her eyes, and something had gone on upstairs, which led her to believe that it was time for me to have the talk with the boys. Now, the talk is complicated enough as it is, but they spoke very little English at the time, and I spoke no Haitian Creole whatsoever. So that made it even more complicated. Now, by now you're wondering why I have brought this up with you. Well, it's because I have learned over the last several years that talking to people, especially non-statistical researchers, about p-values and statistical significance is really remarkably similar to talking to two 10-year-olds about human procreation. Let me illustrate. They thought they knew all about it already because they'd heard about it from their peers. It wasn't nearly as interesting as they thought it was going to be. They stopped listening long before I was through talking to them about it. And if I'm going to be completely honest, they probably understood it a lot less by the time I was done explaining it to them. So that's just my warning to you, is that by the time I'm done with this talk, you may be even more confused than you were when you came in. Also, I have no way of gauging the level of statistical understanding and experience that you came into the room with. So I worked carefully over a long period of time with the education school here to work out a valid and reliable test to make sure that you could understand the presentation that I have for you today. And I was able to do, after much research and experimentation, a simple one-item test. If you're able to understand this test item, you should be fine with this talk today. Good to go? All right, stay in the room then. The ASA issued a statement about 3 years ago on p-values and statistical significance. I'll say more about that in the beginning, but of course, because we were talking about this topic, we needed to have some sort of definition, and so we tried an informal one that says, informally, a p-value is the probability under a specific statistical model, and you read on here a summary of the data, we give an example, and so on. And a 538 reporter wasn't too impressed with that definition. She said it was about as clear as mud, right? One of the people who helped us with this suggested this as an alternative. I'm at Harvard, and there's probably somebody in this room who actually thinks this is clearer. All right, I don't necessarily join you in that feeling. So, what is a p-value? Instead of trying to define it, I'm going to walk through how we find one, and just step through that very simply. So we're a researcher and we know some things, and generally we're not satisfied with that, so we'd like to know some more things. And how do we go about doing that? Well, often what we do is design some kind of experiment to help us know those more things, and then we collect some data from that experiment to accomplish that. And statistician types like to summarize those results numerically, and we'll talk more about that in just a moment. And then from that, we try to figure out what do we know now as a result of that. Let's talk about how we numerically summarize that data then. Well, we typically take that data and we put it into a number that we call a statistic. And then from that statistic, we compute a probability, and that's what we call the p-value. That's what the p in p-value is. And if that p-value is small enough, we call that statistically significant. So those are our two big terms for today, p-value and statistically significant. And naturally your question is, how small is small enough? And typically, historically, traditionally, that's been 0.05 is the cutoff for small enough. So here's an example that comes from the Public Library of Science, Medicine. It's some researchers who were looking at a treatment for a certain kind of renal disease, and that's all I know about this. So if you're eager to ask questions about renal failure and stuff like that, you're barking up the wrong tree. But a new treatment was being compared to a placebo for these patients to improve TKV, which is total kidney volume, which is a measure of health in these kidney patients measured in milliliters. And after a period of time, a year, the difference in median TKV, treatment group minus the placebo group, was about 97 milliliters. There's, for those of you who are into this sort of thing, there's the confidence interval on that. And the p-value was computed for this, rounding off to be about 0.03. So that's the number I'd like you to hold in your head for me, is this 0.03 is the p-value for this. Now we're going to home in on that and talk just very briefly about how we got that number and what it means as we go forward. So for computing a p-value, we have to assume some things. We have to assume a whole bunch of things, actually, but I'm not going to spend a whole bunch of time on those assumptions. But the key assumption is that basically that the treatment is no better than the placebo. Right? That's the key assumption, but by no means the only one. So what does the p-value mean? Well, if that assumption is true, that is, if there's no difference between the treatment and the placebo, one's not better than the other, and if everything else that we assumed is also true, then the probability that we would observe the difference that we got, that is that 97 milliliters, or something even bigger, is 0.03. That's what the p-value is. Now, unfortunately, there's a whole bunch of things that the p-value isn't that people write, say, all the time. And I'll show you a few of them. For example, there's only a 3% chance that the placebo was better than the treatment. Or there's only a 3% chance of getting the result that we did by chance alone. Or I'll use a word that hasn't shown up in this presentation and isn't going to show up anywhere else, but shows up a lot of times in other things because we just didn't have time to talk about it today. There's a 97% chance or probability that the null hypothesis is false. Just don't have time to talk about null hypotheses today. And ... here, because there's a whole bunch of other ways that people like to misinterpret p-values. What can we say when we're talking about a 0.03 p-value? Well, we could have had really bad luck in our sample. We just picked a certain set of test subjects, and had we picked a different set, we'd have got something very different. One or more of those other assumptions that I mentioned could have been wrong, very, very wrong, for example. Remember that one of those assumptions was that the treatment was no better than the placebo. And I do want to mention that even though this gets overlooked a lot, failure of any of those assumptions affects our p-value. So our p-value was 0.03, and Xiao brought me all the way up here from Washington, D.C., Executive Director of the American Statistical Association, to make the keen observation that 0.03 is smaller than 0.05, and so we call it statistically significant. R.A. Fisher, pictured here, the preeminent statistician of the first half of the 20th century, maybe of all of the 20th century, called such results significant or statistically significant. And if back in the day there was such a thing as a undo button, R.A. Fisher would have used it for this. He would have been happy to have a take back on that and call it something else. Because what it meant to Fisher, what he intended to communicate, was that results that were statistically significant were worth further scrutiny. Problem is that significant doesn't mean that to anybody else. In no other context does the word significant carry that sort of meaning. Let's think about that by thinking about the words that are antonyms to significant. Words like, well, insignificant, unimportant, meaningless. Those kinds of things carry a whole lot more weight than not worth further scrutiny. Okay? Let's think about significant used as an adjective. A significant increase. We'd like that in our paycheck. All right? Significant event. I just had one of those in my life. My daughter got married. That was a significant event. Bar mitzvah, significant event. We call people that are important to us significant others. It doesn't mean that they're worth further scrutiny. You've never said to someone you care about, I feel like you're becoming worth further scrutiny to me. I think maybe we should spend a little more time together just to see. Anyway, you get the picture. Words have meaning, and we take that meaning in their context. I'd like you to think about the very first meaning of the word mole that pops into your head, and just hold that. You're not going to be quizzed. There's not a right answer here. Just the first idea of mole that's in your head. All right? Is it this creature that can dig up your backyard? Or maybe it's a particularly well-placed spy. All right? Or maybe it's this thing that you can get on your skin that you probably don't want. Or maybe for some of you, it's Harvard after all. Maybe it's a unit of measurement. Okay? Whichever one it was, in the context of a sentence or conversation, you're not going to get those things confused. But there are many words that we use in statistics, in science, that we have specific meanings for that are used in common language, that when we get those things confused, it's not okay. This is where the title of the talk comes from. Maybe a few of you are familiar with the movie Princess Bride. Then you might remember, if those of you who are, you might remember Inigo Montoya and talking to Vicini, and he says, you keep using that word. I don't think it means what you think it means. If that's a movie, it's a treasure to you like it is to me, what's the word that he's talking about? Inconceivable. Exactly right. Vicini keeps saying inconceivable about things that keep happening, which means that clearly they're quite conceivable. Here's an article from Scientific American, Just a Theory, 7 misused scientific words. For example, the word hypothesis. In science, a hypothesis is a proposed explanation that can be tested. But we don't use it that way in common language. I have a hypothesis about why your mother doesn't like me? Well, I might say that to my wife, but I don't really, it's not really, there's not a test I can run on that, okay? It's not really a testable hypothesis, so it's not really a hypothesis from a scientific standpoint. Theory is another one of those 7 misused words. A theory, like the theory of relativity, is something that is based on, it's substantiated, okay? And so that's why the title of that Scientific American article. If something is a theory from a scientific standpoint, then the words just a theory don't make sense. I might have just a theory about why my favorite sports team chokes year after year after year, but it's still just a theory. But when we're talking about science, that just doesn't make sense. Well, the number 6 word in the 7 most misused scientific words happens to be significant. Here's an example you probably didn't expect when you showed up to this lecture, but I'm going with Tinder, all right? I'm searching through Tinder for a p-value that I might have some interest in that's worth further scrutiny, okay? I come across 0.03. It's kind of a small one. I think I'm interested in it, all right? The proper Tinder response is a right swipe, all right? I'm interested. I want to signal some interest. This is the proper Fisherian interpretation of that I want to investigate this some more. That's what Fisher meant. But unfortunately, over time, statistically significant has come to take on a much more of a different meaning than that. It's taken on the actual meaning of the word significant. And so this, what you're about to see, is kind of a bad Tinder date, a bad Tinder interpretation. This is not somebody who understands what's going on with Tinder, and this is what's happened to statistical significance. Not a good thing. Now, what I want to show you now is that this happens. This isn't just me talking. This is what happens. So what you're going to see now are things that people, real human beings, scientists, researchers, have written in publications because what they've felt like they had to do is to explain themselves because they got a p-value that was bigger than 0.05. These are p-values that are at or near 0.06, and they got to explain this. Why? Because it's bigger than 0.05. Almost significant. Almost attained significance. Almost significant tendency. Almost became significant. Was this aspiring to? Trying to. We're all trying to become something someday. Almost but not quite significant. Almost statistically significant. Almost reached statistical significance. You can feel the yearning, can't you, in that? Just barely below the level of significance. Just beyond significance. You can almost feel it, right? Now remember,
You missed approaching.
We'll get there, Erica. There's more work to be done. These are people who are doing something not because they're strange or not because they're bad people, but they're people who feel like they have to explain something because a threshold is out there, and the question is, why does that threshold need to be there at all? Here are people who have a bigger problem because, and again, you brought me all the way here to tell you this, 0.08 is even bigger than 0.06. So they've got an even bigger problem to explain. So it takes more explaining. a certain trend toward significance, a definite trend, a slight tendency toward significance, a strong trend toward significance. I need to pause here to try to sort something out. So I know some of you, but I don't know most of you, but I can surmise a few things. We have people of different genders, different races, different ethnicities, different political leanings. We have people on the left side of the room, people on the right side of the room. We have people who of various ages. Now, with all these differences, there are probably differences of opinion about how many numbers it takes to establish a trend. So think about for you how many numbers it takes to establish a trend, and then across these differences of age, race, gender, ethnicity, I'm guessing that however many numbers it is inside your head to establish a trend, that number is more than 1. Rant over. A trend close to significance, an expected trend. I knew that trend was coming. Approaching our criteria of significance, approaching borderline significance, which sounds more like a condition to me. Approaching, although not reaching significance. Now, here's where the real splaining has to be done, because we got a p-value that was close to 0.05 but didn't quite get there. Hovered at nearly a significant level. Hovers on the brink of significance. Suddenly we're hovering. We're not in Harvard Square anymore. We're at Area 51 with the p-value UFOs up over the desert. Just about significant, just above the margin of significance, just at the conventional level of significance, because by golly, we needed every one of those significant different digits there. Just barely statistically significant, just borderline significant, just escaped significance, ran right out the door along with one of my lab rats, just failed significance. And thank you so much to Matthew Hankins, who collected all these. May I emphasize again that none of this happens. There is absolutely no need for any one of these sentences to ever be written, much less published, if there's not a threshold sitting out there for somebody to have to deal with. It's not the people that do this, it's the threshold that's put there that makes somebody feel like they have to explain a p-value to someone. So I don't see any little ones here, but if there's anybody else with a squeamish stomach, you might need to turn away from this next slide. Truly, truly scary during this Halloween period. All right, so we have that issue. But we have another issue associated with thinking about statistical significance and p-values and so on, and that is that they don't necessarily answer the question that we're really trying to answer. Because generally, we're trying to answer a question about a hypothesis based on some data that we have. That is, what's the probability that our hypothesis is true based on the data that we've observed? And we can write that simply as, this is about as much notation as we're going to get into here for those of you who don't do notation. Probability of H, our hypothesis, given some data that we have or based on some data that we have. But unfortunately, the p-value isn't that. It's a probability statement about our data given the hypothesis. And those two things are not the same. Okay? If you're not used to writing or seeing things like this, they look like they're the same, but they're not. And so here is a semi-morbid illustration to show you that they're not. All right? okay, this is the one place, Kevin, where there was a little translation error, but it works going backwards, so that's fun. All right, what's the probability that a person is dead? We'll use our D and H symbols here. What's the probability that a person is dead given that the person was hanged? Right? You, and I don't know. I don't have any, I was unable, strangely enough, to conduct any research on that. Tried unsuccessfully on several occasions to get IRB approval for it. So lacking data, I made up a number. Probability of D given H is 0.98. That is at 2% survival rate from hanging. I just made that up. All right. Now we'll flip the problem around. And what's the probability that a person is hanged given that that person is dead? So here's a dead body. And what's the probability that death was the result of hanging? And again, I'm just going to make up a number and say that it's 1 in 10,000. Okay? Now, there's just no way that you're going to flip those two numbers around and get them mixed up. That is to flip the estimate of 2% for the estimate of 0.0001. But unfortunately, that's the common misinterpretation that happens with regards to statistical significance testing, that we mistake the one of those two things for the other. So I hope that wasn't too awful gross. All right. I mentioned earlier the ASA statement on p-values and statistical significance that we published in 2016. It mentioned 6 principles for sort of good practice for using p-values and statistical significance. I'm just going to mention this third one of the 6, that scientific conclusions and business and policy decisions should not be based only on whether a p-value passes a specific threshold. And we actually argued for a long time about whether the word only should be included. That is, we could have left that word out. And I'll argue in a little bit that I believe that we should have left that word out and shouldn't be dealing with thresholds at all. I'll say more plainly that Brightline thinking is bad for science. We just shouldn't be doing those thresholds. And Ken Rothman, one of the people who was involved in thinking about this, says in short in this quote that people have suffered harm because we focus too much on significant results and sometimes too little at looking back on those results that weren't quite significant. So we, my co-authors and I, and others argue that it's time to move on. We wrote an editorial earlier this year and published on the very same day. Some other colleagues in Nature wrote a simultaneous article where we argue that it's time to say farewell to the term statistically significant. It's time to do something different. And why do we say this? Well, I've made several of the arguments that we make already in this talk. That significance has lost its meaning. That the way Fisher meant it to be used isn't the way it's used. That bright lines lead to bizarre behavior. I've illustrated what that bizarre behavior looks like. People have been making the points that we've made forever. We didn't make new points. We just highlighted the points that have been made, but nothing has changed. In fact, there's a recently written article that chronicles how over the decades the problem has just actually gotten worse and worse. And then there's this thing called the file drawer effect, well chronicled by a Harvard professor. The short version of the file drawer effect is that in fact the worst case scenario is that all the wrong answers get published, all the what we call technically type 1 errors get published, and all the non-significant results go get put away in a file drawer. And There's other issues related to publication bias and so on. So why does this matter? Why is this, is this nothing more than just things that professors and eccentric executive directors like to talk about? So let me just give you a couple of examples. There are examples where really nobody gets hurt, but there are, they illustrate how easy it is to move to examples where somebody could get hurt because of scientific potential mispractice. So let me first talk about power posing. Some of you may be familiar with power posing. There was research done here at this university, and then it led to a TED Talk with over 54 million views. And the idea was that by changing your posture, holding your posture in a couple of different poses for a 1 minute period of time, could change essentially your attitude, your outlook, and lead to positive results. And in this study, they found that people who did this became less risk averse when they used high power poses over using low power poses. It resulted in chemical changes in their brain, and led to that TED Talk. So here are what some high power poses look like. Those are high power poses. These are lower power poses. This was the ultimate low power pose in the study. But then some things went wrong when this kind of all went viral. And one of the things that went wrong was that when people tried to reproduce the research, it didn't reproduce very well. That people tried to do this again and with other subjects, and it didn't work so well. And basically, there were several things that were wrong, but bottom line is there was too much dependence on statistical significance in there. So we found statistically significant results and got all excited about that without necessarily thinking about the other sorts of things that you need to think about, which I'll illustrate on the next slide. And I want to emphasize here that these weren't bad scientists or people committing fraud or doing anything like that. It's just simply that these are complicated problems, and, well, human beings are complicated beings. And so you do a study and you see something interesting, and that's when you really need to apply Fisher's principle of worth further scrutiny. The results that were found were interesting. They were interesting. They did this and something interesting happened, and so further scrutiny should have happened. In my opinion, further scrutiny does not equal TED Talk. Okay? It equals more study, then maybe TED Talk. All right? In the article that in the American Statistician from March 2019, where our editorial is published in 43 other articles, there's this article from McShane, and here's where they say what good practice should look like from a statistical standpoint. When you see an article like this, you need to think about everything else. You need to think about all the other prior evidence that's out there. How plausible is the mechanism that goes from standing like this to having a better attitude? Okay? Think about all the other issues that need to be thought about, and don't just think about p-values and statistical significance. The problem is that, as Joe Palca says, science works in increments, but the media loves to go in leaps and bounds. So here's a second example. This comes from the wonderful Last Week Tonight John Oliver program from a few years ago. I highly recommend this scientific studies episode from John Oliver. It's loaded with the F-bomb. it's also loaded with spot-on analysis of what's right and what's wrong with scientific studies. And there's the headline that was all over the media: glass of red wine equivalent to an hour of gym time. All right, who doesn't want to believe that, okay? That's just, that just sounds great, because on all those days when when it would be much easier to have a glass of red wine instead of going to the gym, all those days, such as days that end with the letter Y, okay? You want to believe that, all right? So let's go to the actual study. So resveratrol may be natural exercise performance enhancer, okay? By the way, this is what it looked like everywhere was reported in the media, okay? So the press release headed, natural compound found in some fruits, nuts, and red wine may enhance exercise training and performance, all right? So dig a little deeper, and so in the key point summary of the research, it says that resveratrol, an antioxidant found in red wine, has beneficial effects in cardiac and skeletal muscle function, similar to the effects of endurance exercise training, all right? An antioxidant found in red wine, okay? So not the red wine, but the antioxidant found in there may be helpful. Combining resveratrol supplementation with exercise training augments the beneficial effects of exercise alone. So, in other words, not a replacement for, but combining with. That wasn't reported in the media studies. We show that endurance training in rats. Okay? That's a little detail that was not mentioned anywhere in the studies. And then these other details I highlight in green are all the things that are totally associated with statistical significance. That we show, associated with, our results establish, are the things because they found small p-values. And quoting from the press release, and I want you to see this here, even in the press release, they're not talking about you or me skipping the gym and having a glass of red wine. They're talking about maybe this work might help people who are otherwise physically unable to get to the gym. They hope that maybe this research could help those people, like maybe people with severe issues with diabetes and things like that, maybe those people. But by the time it got through the press release mill and out to the general public, that's not what appeared at all. Here are 5 words. If you take nothing else away from this today, here are 5 words that you should greet with healthy skepticism. In a groundbreaking new study. And you know what? I got all the way to Harvard touting my skills at being able to count. How many words is that? Is that 5? Good. I was hoping I could count. Remember that one study is rarely enough. The words "a groundbreaking new study" might be loved by news writers, but must be resisted by researchers. Breaking ground is only the first step in building a house. It will be suitable for habitation only after much more hard work. Everybody's been somewhere where the house got started building and didn't get finished for some reason or another. For those of you who are into this sort of thing, these are the graphical results from the resveratrol study on rats. I'm not expecting you to read this or even be able to see it from some of the places where you're sitting. For those of you who are into this sort of thing, I just want to make the observation that the researchers were a little too excited about the places where the asterisks showed up. Those are the statistically significant parts, and not paying nearly as much attention as they should have been to how much difference there is in the size of the bars, which is where the focus really ought to be. I'm going to finish up now with one last observation. Recently, within the last couple of years, there's been a suggestion that one way to deal with all of this, or at least in the short term, to deal with all of this, is just to change the bars a little bit. Instead of going with p less than 0.05, to go with p less than 0.005. This has been suggested as a way to address this threshold problem, at least in the short run, for at least some areas of science. And it was suggested by a whole lot of smart people I really respect. In this article in Nature Human Behavior, and then very shortly afterwards, rebutted by a whole bunch of people, who I also really respect. And without any false modesty, all of whom are smarter than me, and I'm going to step in the middle of it anyway, proving that I'm not very smart, with a fall classic illustration. This is a moment that's near and dear to me. I'm a lifelong Kansas City Royals fan, and this is a picture from the 1985 World Series. Now, I do want to take a moment to acknowledge that I have caught on that I'm in Boston. So I do want to say that in my office, and I can prove this because I have a picture on my phone, I have a photo of the 1975 World Series, a signed photo of Carlton Fisk willing his home run to stay fair. But this is the 1985 World Series. It's the bottom of the ninth inning of Game 6. The Royals are down 3-2 to the Cardinals, and they're down 1-0 in the bottom of the ninth. George Orta is the batter. You see him crossing first base there. He's hit the ball to the first baseman, who has tossed the ball to the pitcher, Todd Worrell, and in time to throw out George Orta. These plays at first base, for those of you who aren't into baseball, are called bang-bang plays when they're real close, and the umpire has to do something that's really quite physically impossible. He has to see whether the ball gets into the first baseman's mitt before the runner's foot hits the bag. Because our eyes can't work like that, the umpire has to actually listen for the sound of the ball hitting the glove and the sound of the foot hitting the base. Well, George Orta was out, but umpire Don Deckinger didn't see it that way. He called him safe. This is well before instant replay was allowed to overturn the call. George Orta was called safe, thankfully for the Royals, not so thankfully for the Cardinals. The Royals went on to score 2 runs to win Game 6 of the 1985 World Series. The next day, they also won Game 7 of the 1985 World Series and became world champions. Now, long before I started thinking about p-values and statistical significance, I was interested in solving this problem of close plays at first base. And I came up with what I'm sure you'll agree is an elegant solution to this close play at first base. Very simple, and it seems to me very similar to solving this p-value problem by changing 0.05 to 0.005. All you do is you move first base 3 feet farther down the line. Now, even Don Deckinger can see that George Orta is out, assuming, of course, that Todd Worrell steps on the right base, all right? All you do is move the base 3 feet farther down the line. No problem, right? What's the problem with Ron Wasserstein's elegant solution for this? Well, obviously, the problem is that play is no longer a close play, but they'll just be close plays 3 feet farther down the line, right? There'll be a few fewer close plays, but they'll just be close plays a little farther down the line. Except that, I'll argue that it changes things a little bit more than that, because here we have beautiful Fenway Park, and I argue that changing from 0.05 to 0.005 is moving first base bag not just 3 feet down the line, but kind of all the way down the right field line. which then changes how the entire game is played. All right, so let's wrap up here. We argue that it's time to stop using statistical significance as a metric for scientific inference. We don't actually need it. All the information about significance in terms of what's worth scrutiny is already in the p-value. It's there already, so we don't need it. My colleagues and I and many other people have written a lot about what a world without that term would look like. P-values are still useful. They have all that information there, so we don't need to do that. And statistics is just as important. Indeed, it's just as significant as ever. It's consistently rated as one of the very top jobs. Thanks for giving me this opportunity to tell you about it.
We have time for questions.
Yes, sir.
So as you point out, the real problem is the thresholding. It's what I call black-white thinking.
Right.
The truth lies on one side of any barrier, whether it's 0.05 or 0.005 or what have you, and falsehood lies on the other. So if we all agree, we can all agree on that, and we can even say we shouldn't do this anymore. But human beings still love to do this, right? So what are the things you found to get your students out of this black-white thinking?
Okay, so could you hear the question? All right, so in short was, if we can agree that thresholding is a bad idea, what do we have to do to get students out of the black-white thinking? So I don't know what it's going to take to change how we teach this stuff, because it's deeply embedded in everything that we teach in statistics. And I don't claim any special expertise on how to do that. So we have started a significant amount of work on that by reaching out to the statistical education community to ask the people who are experts on statistics pedagogy, how do we make those changes? And there's a large community of people trying to figure out how we do that and what's the best way to communicate those things. And I really don't know that. But I want to answer also a slightly different question than that, because there are two aspects, at least in my mind, and they're not completely separate. There are two aspects to the decision-making process. The one aspect is evaluating the strength of the evidence that you have, and the other is then making a decision. So I might be trying to figure out whether that drug for renal disease is effective or not. And so on the one hand, I have to evaluate how strong the evidence is that I have from the experiment or experiments that I've done. And I would argue that that strength of evidence that I have is not a discrete measurement. It's a continuous measurement based on some scale, which a p-value is a continuous measurement. At the end of the day, somebody has to make a decision about whether to use the drug for a particular purpose or not to use it, and that ultimately is a dichotomous decision, although it might be dichotomous for me if I'm the person with the disease and need to know whether I'm taking the treatment or not, but it might not be a dichotomous decision for all patients, and so that moves into other kinds of decision making, like decision theoretic approaches or whatever. And so that's another aspect to thinking through how we use the data once we have it. Yep. And then I'll go to you next. Okay, I'll get you in the back next after I get this person. Yeah. All right, other way around then. All right, go ahead. Yeah, go ahead.
Yeah, two questions. First, do you think that looking the things in a more Bayesian way helps with this? That's one question. And the other is that in terms of reporting, would it should we add more structure into journal articles? That's the way that since 65 until now we've been adding a method section and this section, something that in report that it forces you not to say, give those words, and it shows you more how you should report a study in a way that doesn't add this type of...
Right. So I'll do those in reverse order. I think that I'm not sure exactly whether I would say more structure, but I do think that journals should provide more guidance with regards to this, and some journals are starting to head in that direction. And without necessarily totally giving away my biases, yeah, more Bayesian stuff would be great. And yeah.
I was wondering how you relate this to the other
You can do that, yeah.
issue, which is oftentimes when, researcher A does a study, they find a certain, if you look at effect size, they find a certain effect size. It's very well known that even if it's replicatable, often the effect size shrinks, even if it stays, quote unquote, statistically significant. And it seems to me that a lot of this is actually done through cherry picking. In other words, as you were saying, the study that stays in the drawer because it doesn't have an appropriate p-value. And, if you go to the, if you're a hard-nosed frequentist, you shouldn't, you do your test, you have your test, you get your results, and you go ahead. But, I mean, realistically, we all know that people cherry pick like crazy.
I have nothing to add to that.
Next question. We still have time for
Yep. Yes.
Thank you for the talk, and I've been hearing similar things as you presented, that these are the places where probably using p-value or using a threshold is not the right thing to do. So I'm going to flip the question a little bit and ask you in what context, or when you're doing a study, one should be reporting the p-value, or what sort of information is that carrying? I think because a lot of times we're told don't do this, but then it also kind of made me wonder in what context are we actually able to get more information by looking at this particular statistic?
Right. So I think in all contexts where you're doing this kind of statistics, you should be reporting the p-value and all the other stuff that all the other statistics that all the other descriptive statistics that you have. And in the articles that that I and others wrote in the on the March issue of the March 29 issue of the American Statistician, there's a lot about that. We should be as transparent as possible about all of our statistics, about all of the things that we did to get there, so that others could arrive at the same numbers that we got, because they know everything that we did to get from data to the statistics that we got. All of those things are there. The argument that we're trying to make is that by not focusing on thresholds, scientists can focus on science, because we get back to making arguments about why the science is what it is, and not trying to get to some arbitrary threshold, to some arbitrary line that we're trying to push this statistic across so we say that we've arrived at truth, and instead look at what we have gotten and see where we are. We knew some stuff, we got more information, now what do we know, and what do we have to do to find out more?
Yes, Gary.
Hi. So, I mean, there has to be some quantification of uncertainty in clinical journals, at least.
Right.
And so, p-values, I haven't seen much of anything written about the choice of the 95% confidence interval, the thresholding that's effectively going on when you choose a level of a type 1 error that's the basis of the construction for a confidence interval. Do you have any thoughts on that?
Right. So the question was, if you pick a 95% confidence interval, choosing 95% as your level of confidence is as arbitrary as picking 0.05 for your significance level. And so what are my thoughts on that? Well, obviously one thing you can mark is you can choose it, publish multiple levels. But I think the better solution to that is to stop thinking about the things that are just inside the confidence interval as being very different than things that are just outside the confidence interval, and to and when thinking about the confidence intervals and talking about those, to talk more about like, for example, what both ends of the interval mean, not just whether the interval contains 0 or certain values or not. All the things that people have been doing oddly with confidence intervals forever, to think about what those things mean. For example, I went flying by, because I had to, that confidence interval for the kidney disease measurement, and 97 was the median. The confidence interval went from 11 to 182. That's what was really interesting for a statistician, and should have been really interesting for a scientist, because. And again, this is, the level of expertise you brought all the way from Washington to here. There's a lot of difference between 11 and 182. Mama brought up a boy with a thick noggin. So that's what, but if you were to go back and read that PLOS article, there is no mention of that. And this goes back to the question I was trying to answer for the gentleman in the back. If we were not so focused on statistical significance, I'm convinced that that's what a scientist would be trying to answer then. Be trying to look at is what's going on here with 11, which probably, I don't know anything about total kidney volume and how important that is, but my guess is that 11 is probably not that big of a deal, and 182 probably is a big deal. And I'd want to be talking about that, but I stopped talking when I got statistical significance. That was good enough. And that's what's evident in that article, if you do read it, is wherever I got statistical significance, hurrah, and that's what we talk about. And where I didn't get statistical significance, we stopped talking. And instead, we ought to be looking at those effect sizes and talking about those in the context of our p-values and our science and everything else. And really, we should have been paying attention to that confidence interval for sure. And so that's kind of what that illustrates that whole point, but didn't really have time to go there. So thanks for giving me a chance to do that. And I do want to say there was a remark made up here when I indicated that I have a certain Bayesian tendencies in my thinking as I've gotten older. Yes, you can make all the same mistakes with Bayes that you can with frequentist thinking if you let yourself do that. You can throw thresholds at things. Don't do that. Don't do that. Yeah.
So I wonder about two things. First of all, does this push every paper towards meta-analysis? Always, so that they don't stand alone as much anymore, right?
Yeah.
And then the other thing which is associated with this is whether you, how do you, so too many papers are still in some senses too long. How do you come to a succinct conclusion? And I think that's why people have loved the cutoff, is because it's a communications device. You argue that that's misleading, and I think that's well taken. But what do we substitute for a succinct summary of what's been found without that?
So there's two questions, and I'll do the second one first. The cutoffs a handy way to make papers succinct. And there's already a lot of worry about too many papers being too long, and if you've ever been a reviewer for a paper, which I know many of you have, the last thing you need is longer papers with longer explanations and so on. And what recommendations do we have? Well, I don't have real tangible ones right now, but we do have some people who are doing some thinking about how to, maybe rewrite papers in this era where you aren't just saying, hey, statistically significant, and that's good enough. But we steadfastly refused to try to write sample sentences because we easily imagined that there would just be this whole generation of papers that just copied our sample sentences, when what we wanted people to do was actually think about their results. And so we didn't do that on purpose. And the first question, meta-analysis, yes. So what do I think about meta-analysis, and was that become more important? And meta-analysis is really important, but meta-analysis also has the worrisome problem of it's meta-analyzing all those papers that got published. And unfortunately, all those papers that didn't get published, you have the publication bias problem feeding right into your meta-analysis, and that becomes seriously problematic then. Yep.
I have one more question. You're the executive director of the American Statistical Association. What comment do you have about co-publishing a journal called Significance?
I appreciate that question.
You definitely won this.
So first of all, let me say that I am extremely proud of that journal. And if you don't receive it, then you should join the American Statistical Association, if for no other reason than to get the best, most readable general publication on statistics that's available. And we had a long conversation about whether we needed to change the name of that journal in light of this. But as I mentioned on this slide, we'll never see it again. Statistics is still remains a very significant discipline. So I'm sticking with that. Thanks for asking. Enjoy your magazine.
So
Yep.
the ASA formulation that you put up sounded quite much weaker than compared to the talk that you gave us in terms of recommending how to use p-values. Can you tell us a little bit more about the negotiations that went by when you sort of opted for that formulation?
Right. So the question was, the ASA statement, he said, sounded weaker than the formulation that I brought forward to you today. Can I say a bit about what led to that? And absolutely I can. It gives me the opportunity to tell you very briefly about the difference between the two things. So the ASA statement was the result of bringing together a large panel of experts who basically argued, and boy, did we, until we reached the point where we could settle on things about which we felt that not only did these experts agree on, but that they felt that there was broad agreement on. So they felt like these were the 6 principles on which there was general agreement in the community. And so that's what got published. And that's where that is. But we knew when we published that those things gave great advice about what not to do when using p-values. But they didn't say very much about what to do, what researchers should be doing. They only told them what not to do. So we proceeded over the next 2 years after that to gather people in various ways to talk about what good practice would look like. And we had a conference, we called for papers, we edited and curated a collection of papers, and in that process, I and my two co-editors came to what we felt like in our professional judgment, and this is not an ASA position now, this is just our professional judgment, we felt like was the inescapable conclusion is that we just can't go on continuing to do business as usual, which is to continue to use statistical significance the way it's been used. And so we published that opinion. And so that's the difference. The one is a statement approved by the ASA based on kind of the least common denominator kind of thing, and the other is sort of an updated version based on a whole lot of thinking by some people, but it doesn't represent as broad a consensus as the other statement does.
Take a final question.
Final question. You didn't get it from him, did you? Okay, no, it's all right, thanks.
So, my question is, when it comes to birds and bees, people tend to figure it out. And by the way, it's also part of the required curriculum in K through 12. It's actually part of the wellness curriculum. I'd like to ask, what's being done to make sure that statistics is part of that required curriculum, so that publicly things like that you showed, with the red wine would just be completely discarded, disregarded, and ignored, which is currently not happening.
Can I give him my copy of the?
That's a great question.
That is a great question. So the question was, actually, will you say that question for everybody?
Thank you. First of all, thank you very much for the talk. I really enjoyed it. Gav Abrahamian from the Harvard Business Analytics program. My question is really simple. I love statistics, and I love more people to at least like and enjoy and understand statistics. And my question was that when it comes to birds and bees, people figure it out. And actually, it's part of the curriculum in K through 12. And it's actually part of the wellness curriculum. So by the time kids graduate from high school, they have some level of understanding of wellness. But statistics is an elective. And when I heard about that it was an elective in my son's high school, I was just appalled. I thought it should be part of the math curriculum and not starting at the high school level. I felt that it needed to start from much younger age so that the general public understanding of statistics could be much, much greater, and the scrutiny of all of this stuff that's being thrown upon us by whether it's the media or other outlets could happen at the much wider level by the public and just set aside and discarded and ignored, and it would just disappear. Thank you.
Okay, thank you. I knew I couldn't say that as well as you did.
And I do have an actual copy for you.
Oh, thank you. Glad to talk to you more about this. Here's the quick version. It is an enormous problem. The challenge of the problem is that we have such a highly decentralized educational program in the United States. All the states do things their own way, and within the states it's often even more decentralized than that. The American Statistical Association is highly committed to addressing that issue, and we show that commitment in all kinds of ways. We have staff that's designated to address that. We have a whole lot of member volunteers who are focused on that. We have curricula guides for K-12. We have developed the guides for how to teach teachers how to teach statistics at the various levels that we provide to all of the teacher training programs at colleges and universities across the country. We have workshops for teachers to teach them sort of the latest pedagogical tips and tricks for better teaching statistics at various levels. And we have worked with state supervisors of education to try to get them to then to carry that stuff out to when they go teach their teachers. All of that said, much of the time it feels like we're trying to, you know, drain the ocean with a bucket or whatever the right metaphor is. That it's an uphill struggle, and there's constantly other things that people are trying to insert into the K-12 curriculum that competes with statistics. Many other disciplines feel like they are essential to the K-12 curriculum, and they're winning in some of those instances as well. I don't want to name names because then I'll start some kind of fight in this room, which I'd rather not. But you're right. It is important. Statistical literacy is important, and that's we literally are working on that all the time at ASA. Thank you.